Hi everyone, we are here at Evergreen State College still. It's very beautiful here, and I just want to tell you about NMR today. So NMR is nuclear magnetic resonance. It's a technique that we use to figure out the structure of molecules. So I heard about this funny story way back in the day. There were some physicists who took a magnet and they bored a hole through it, and then they took mice and put them into that hole, and then they tried to collect valuable information about it. That research wasn't really taken seriously at the time, so it made its way into a journal that was, just sort of fluff science or whatever. And then it turned out that that's the basis of what we know today as MRI, magnetic resonance imaging. So you see pictures of people who lie down and they get put into this device, and that's actually a magnet. So, and using that information, we can detect cancer cells or all kinds of things. So it's really amazing how that wasn't taken seriously back in the day. And MRI actually is named that because nuclear was sort of has bad connotations, so that's why they renamed it. But MRI is based on NMR, basically nuclear magnetic resonance. And how that works is considering that nuclei have these particles, protons and neutrons, and those nuclei have a spin. We've heard about electron spin before, so electrons have a property called magnetic spin, and so we think of spin up or spin down, and we pair those when electrons get together in an orbital. All right, well, nuclei have a property called spin as well. Now, it turns out that when you have isotopes that have even numbers, like carbon-12, they tend not to have a spin, but nuclei with odd number mass numbers do have a nuclear spin. And so the isotopes that we usually study are carbon-13 and hydrogen-1, but we also have other choices for isotopes as well, phosphorus, sulfur, other elements that exhibit a nuclear spin. But these are the most common ones. So when you look at a nucleus and it has this property called spin, what is that? So it's not that it's actually spinning, it's just this property that it's got poles. So think of a magnet. So you've got a north pole and a south pole, and then there's these lines of magnetic force that emanate from there, okay? So when you think of a magnet, okay, when you have just like a pile of magnets, let's say they're randomly distributed, so they're going in all different directions right here. Well, when you apply an external magnetic field, that will cause each of those individual magnets to align. So instead of magnets, though, remember we're talking about nuclear spin. So let's say we have nuclei, and you apply an external magnetic force, that's going to cause the nuclear spin to align, either so the poles are this way or flipped. All right, so let's say that the applied magnetic field is shown by these arrows. So basically the external magnetic field has a pole going this way. And let's say that each of those individual magnets or nuclei can either align with the field, in which case they're called in the alpha state, or they can be in the opposite configuration, which is called the beta state. Now you can see already if you're aligned with the field, you're going to be more stable than if you're aligned against the field. That's going to be higher energy. So if you sort of map that in an energy diagram, you could say the alpha state is lower than the energy of the beta state. So if you have an external field like this, external field, and we usually use a beta as a symbol of magnetic field, you could be with that field, same orientation, or you could be against it. So there's this kind of energy change associated with those two states. So that means if I put energy in, let's say like this, I put energy into this electron, I could potentially flip it so that it's the other way now. Or another way to think about it is conservation of energy. This spin, if I let it relax, it'll come down and it'll flip and it will release that delta E amount of energy. As the radio frequencies come in to that amount of energy that corresponds to delta E, I said that we would flip these spins in reverse, and also that these spins relax back down to the alpha state again. And when it flips down to the alpha state, that's when we get a signal coming out corresponding to that delta E. Now, this process here is what is referred to by resonance. So that is the R of MRI and the R of NMR. Okay, is resonance. And that's the idea that you have this special delta E that causes these spin states to reverse. Now that delta E then gets measured. So these energies that come out, you have different delta E's for different protons. And those get received by a receiver coil, so that accepts the signal, and then it goes and gets analyzed further by computer software. So let's talk about the source of the delta E's. So you know that the nuclei are charged particles, and so they interact with an external magnetic field. So let's say that you put a magnet up to a molecule, and what happens is that the electrons start moving. So you've got these electrons around the nucleus, and you start to get electrons moving, and then that induces or causes another magnetic field. So that's called the induced magnetic field. So this is coming from the atom in response to the external field. Now ultimately what we are probing, what we're trying to measure is how much this nucleus feels the external field down here. How much does it feel that? Now, a lot of factors can influence that. One of them is how much this electron is covered by electron density. So if you picture electron density around here, then it's sort of like a blanket, right? And so this field will not be felt as strongly. But if the electron density is pretty sparse, or maybe it's being pulled away, to over here because of something electronegative, then it's going to feel the field more. And that's called being de-shielded. And here the opposite case was where we felt more shielded by additional electron density. So based on how much these nuclei are shielded or de-shielded, you're going to get different delta E values here. So here's how we do that. We have an instrument with a very powerful magnet in here, usually many times the strength of, like 1,000,000 times the strength of the magnetic field of the Earth, okay? And that magnet has a hole in it, and so you have a sample tube with the molecules you're interested in analyzing that goes into the magnet, and it spins, and as that spinning sample goes down into the magnet, we use a radio frequency pulse. Okay, and so what that is radio frequencies are the frequencies that tend to correspond to these delta E values. And once you excite those nuclear spins, then you let them relax down. So as it relaxes, there's this signal that gets sent to the computer, and you can see on the screen that it looks like this. It's a very complicated signal. So what happens here is I collect some information in the form of a free induction decay, which is a complex signal here. And that tells me how let's say I have a hydrogen 1 probe in here. It tells me how the hydrogen 1s are giving off these signals based on their electronic environments. Now I can then process that using a mathematical operation called a Fourier transform, and that will give me some simplified data, so a different way to look at the data. So I get actual peaks from this very complex signal here. And so this is what an NMR spectrum tends to look like. At a basic level is just an x-axis, which we call chemical shift, and it's in units of parts per million. And then we have intensity in the y-axis. So chemical shift is this property that is based on basically the idea is that there are many different strengths of magnets. So our magnet has an operating frequency of 90 megahertz, whereas the NMR at Seattle University is 300 megahertz or 400 megahertz, okay? So that sort of tells you about the strength of the magnet. So at Seattle University, they have a much stronger magnet than we do. But I want to be able to find a way to compare data across wherever it comes from. I don't want to worry about what magnet was used. I just want some data that's consistent. So regardless of which magnet is used, I should be able to say this signal at 5 ppm corresponds to the same signal that they get at 5 ppm as well. It's just that because they have a stronger magnet, they have more resolving power. That is, their peaks are clearer and easier to distinguish from other peaks. But the idea is that I want the x-axis to be normalized. So whenever I'm talking about ppm, it's standard. So common solvents used in NMR to get samples in solution form cannot contain the isotope that you're studying. So otherwise they'll get picked up and you'll see signals for the solvent, and usually you're not interested in that. So for example, if we're using proton or H1 NMR, we call it proton NMR by the way, then we want to make sure we don't have hydrogens. So let's talk about this. Deuteria are used instead, and they are a type of hydrogen, but they're hydrogen too. Then we take common solvents that are used, and notice they can be very polar or very non-polar or intermediately polar, and we want to have a variety of solvents we can use to make sure that we can dissolve our samples. So you can have deuteria instead of where hydrogens would normally be. Again, the reason for that is we don't want to see peaks for solvent. We're interested in studying a molecule, not the solvent molecules.